more obvious. I didn't realize that was.
Sean, the last project, is it more or less like this last one that we did?
No, it's not. Well, it's hard to say if it is or
It's
isn't.
a little bit more convoluted.
It's even less math than this one.
Okay.
No, it's less math than the one you just did.
Uh-huh.
It's all about setting up a 2x2 table and then pulling numbers out of that table and making probabilities from. You're analyzing false positives and false negatives from basically drug tests, disease tests, doctors understanding disease tests and things like that. It's one of my favorite projects because of that. Yeah, it's one of my favorites because of that. But it's much less math than the one you just did. I like ending with that one, and students, it's the one, I think I told you guys, it's the one that let me calm my neighbor down using mathematics. She had tested positive for Down syndrome and an amnio draw. Did I tell you this?
No.
It's in your project. You'll see it when you do project 4. She had tested positive for a Downs test and an amnio draw, and she started freaking out. I'm like, let's just sit down and let's work the numbers, and let's see how likely it is that your fetus actually has Down syndrome. And it ended up being, you'll see, it ends up being like a 0.999999 that the baby was fine. And she's like, well, why did I test positive? Like, because you're not at risk. You shouldn't have taken the test in the first place. The test is for at-risk mothers. You're not an at-risk mother. Why would you take the test? Because my doctor said. I'm like, yes, but the doctors, as you see from the problem right before that one, generally don't understand what a false positive means and how to interpret it. So that's why I love this project, is it gives you guys a tool to take with you when you go to the doctors. And doctors generally hate me because I ask these questions all the time, and a lot of times they don't know how to answer them. That's why I'm so glad I got medical people in here learning this stuff with me. That's why I'm so glad when I see medical people in this class, I get stoked. Remember Max's second checkup?
Yeah.
What are you feeding your child? You wouldn't ask that question if you understood statistics, would you? Right? And you rolled your eyes. I remember the day. You rolled your eyes that day, Davida. I remember that. Because you were like, oh, God. Because you knew. You knew how ridiculous that question was. That's why I love that last project. It's a great way to end the course with. And it also gives a nice footing into 244 should you go there. Type 1 and Type 2 error. But it attacks it in 243 in case you don't go to 244. So, good stuff.
It's too bad.
That's okay.
Almost make me want to go to do.
It'll always be here if you need it, my friend. It'll always be here if you need it. Not to worry. Not to worry. Okay, friends. What I want to do now is set the stage for using these curves next week. And it's going to take a while to develop this, so let's take the time today. We're going to want to use our TIs today, too. I gave you guys all those programs. There's another program in there. You don't need it right now. Just make sure we've got it with us eventually. I'm thinking about half an hour or so we'll get into it. There's another program I gave you called Stanormal, and that's one of the ones we're going to want to use soonish. I'm thinking about half an hour or so. So what I want to do right now is I want to compare and contrast a bell curve with a normal, I shouldn't say normal, with the distributions we've been looking at. Up till now, we have been looking, and I say this is like the past 2.5 weeks, probability distributions. Okay, probability distributions. What do you remember about them?
They're fun.
They're fun. I like that. I agree. They're fun.
The X and then the P of X.
Thank you, Alicia. The way we've looked at all of them, whether it was chickens, whether it was Sarah Palin, whether it was the Gambler's Ruin. Anybody do the Gambler's Ruin quiz for this week?
Right.
You tried? It's okay.
I started.
That's okay. It'll be there if you want to. I'll put the solution video up so you can see it. All of those distributions, no matter what the chuck-a-luck, doesn't matter what the distribution was, they look the same. There was an X column, and there was a P of X column. And it was a t-table. And you filled it up. You filled it up with the X values, the random variable values, and you filled this up with the probabilities. Tell me about these again. There was something special about these, weren't they? Yes, thank you. These always sum up to 100. Remember that? We used that quite a bit. Life insurance. Oh yeah. That's exactly right. We used it with life insurance quite a bit. We used it with chickens even a couple times. So that was we were able to find the average. Yes. We were able to find the average by doing the sum of this times this, the whole, and we got the standard deviation. Don't worry about those formulas. That's not important. What's important is understanding what that was. Now there was something I was withholding from you, and you're about to see why. Suppose leave some space next to this. Actually, you know what? Don't write anything right now. I want to lead you into why we have to get this bell curve. Yeah, right now. Just so this is good. Clear. Suppose Suppose, remember the data sets I showed you earlier? Heights of American women,
Yeah.
IQ scores, and LDL readings, volumes of gas tanks, number of chips. That's not a very good example, but volumes of gas tanks, thickness of tree bark, times of eye contact with schizophrenic patients. Let's pick one of those that we think is kind of fun. Scott, you're right.
We love the crazies.
That's good. Times of eye contact. Okay, go ahead and give me a value that time could have.
12 seconds.
12 seconds. 5 seconds? So you schizophrenic patient, you make eye contact with them. How long could that eye contact last? Probably 0 is the least amount of time, right? Technically speaking. But we'll start with 0. We'll put this in seconds. 0. 1. Stop right there, though. Stop right there if you'd be so kind. Oh, now it gets interesting, doesn't it, Joanne? Because if we were buying birds in a store and keeping track of how many girls I got, or the likelihood of girls, I could have 0 girls, I could have 1 girl, I could have 2 girls. But I can't say, go.
I could be sitting there and I could talk to her for 20 minutes and she might be schizo.
No, that's a different question. We're not trying to identify.
No, I don't.
Good, possible. But you guys are, you guys are answering you're asking and answering a different question than I'm asking. I'm saying, assuming that you are with a schizophrenic patient that has been properly diagnosed with schizophrenia.
She doesn't have schizo.
Leave Andrea alone. It's got nothing to do with Andrea. I said your name on camera. I'm sorry, Andrea. The question, Taryn, what are you thinking of? Are you sure? What are you thinking of right now? This is the problem. It's the type of data. Aren't there times between 0 and 1 second?
Yeah.
So, for example,
3/4 second.
isn't there a half a second?
There's like a 100.
Wait a minute. Even that's not even right, is it? Let's put 0 and 1 down here.
Isn't there an infinite amount?
There's an infinite amount of time between 0 and 1. There is not an infinite number of girls between 0 and 1. Matter of fact, there's nothing between 0 and 1. For what kind of data? Starts with a D. You haven't talked about it in weeks, although we've been using it. Discrete. We have been using it for weeks now, but we stopped calling it discrete data because we just were using it. This is now continuous. And that's why I bring the normal distribution in, because it's the most prevalent, continuous dated distribution. So the binomial is the most prevalent discretely valued distribution. That's why I told you to leave space for this. This only works when you have discrete data types. Discrete meaning you've got whole numbers of possibilities for the random variable. 0 girls, 1 girl, 2 girls, 3 girls. I'm not saying the average can't be 0.8, but the data values themselves cannot take on fractional or continuous values. But then you start measuring things. Ages, heights, weights, blood pressures, cholesterol readings, thicknesses, times, temperatures. And those things have sliding scales of measurement, don't they? All of a sudden, the question, what's between 0 and 1 here? Nothing. What's between 0 and 1 here? Everything. More than you can even count. Now, of course, Sandy's going, there's a limit to that, of course.
No, there isn't.
There is. Your precision of the instrument you're using to measure it.
Exactly.
Right? Your machine maybe can only measure to the 10th of a decimal place. In which case it would go 0, 0.1, 0.2, 0.3, 0.4, and then technically it would be discrete. But it's still more discrete than pure discrete, even in that. Just because you can't measure it doesn't mean it's not continuous. It's still just because you can't measure it with enough precision doesn't mean it has more precision. You're just unable to catch it. That's why they build better and better machines. Right? I went to OHSU a couple weeks ago to be with my father-in-law, and seeing some of the early machines they use. They have a great hallway there showing me. It's amazing to see those early machines they used to do medicine with. The precision was not very good at all, but they were still able to do wonderful stuff because that was state-of-the-art technology. What's it going to be in 20, 30 more years? God knows. It's going to have decimal places more precision, which is phenomenal. You remember what precision costs, though. Remember the pumpkin project from two back projects? How many seeds do you have to plant? It took 13 seeds, if my memory serves me correctly, to get 99.999% precision, and it took 18 to add 2 more 9s. So to add 2 more 9s, it took 5 more seeds. It would take like 10 more seeds to add 2 more 9s to that, because you're getting out in that tail. That precision comes at a great, great cost. But that's what drives things like medicine and better medical treatment. I'm getting inside of myself a little bit now. So I think this is a terrible way of talking about continuous data, because we'll be drawing numbers forever, and that's silly. What did we invent to deal with that mathematically?
Infinity sign.
Well, that doesn't deal with it. That avoids it, actually, believe it or not. I love that, though. That shows us that it goes on
I
forever.
learned how to draw that stupid thing in math for so long,
We can draw it again
and
today.
now I can't use it.
Blink. There you go, good, thank you. She didn't blink for like 3 minutes. No, that's good. We can use it, and it exists, Riley. It does exist. No, it does exist, my friend. You're awesome. It does exist, and it's part of this, because theoretically speaking, there's no top end to those times, right?
So is it
We could sit there and be with that schizophrenic patient making eye contact infinitely.
Which one?
Technically, right? Say that again.
Which one?
Which one what?
Schizophrenic.
I'm confused.
Isn't that not her multiple personality?
I'm just saying, the time itself can go off to infinity. But dealing with those numbers, I don't want to deal with just the top end or the bottom end. I want to deal with the numbers in between. What did mathematicians invent to deal with the infinitude of the numbers between integers? You're thinking too hard. You're thinking too hard. You're thinking way too hard. It's okay. It's okay. You're thinking so hard because you've forgotten the most basic component of algebra class. The number line. You're forgetting the most basic component of algebra class. Everything sits on the number line. And of course you've forgotten about it because you haven't used it in here very much. We've had no need to. Everything we've been dealing with has been discrete for the most part. But say that again?
But why start now?
Well, because you have to. Basically, what happens when you encounter continuous data? You can't do it this way. We now need to. I start talking about IQs, you guys are like, oh, IQs are interesting. Okay, but how do you get an IQ? What's an IQ score?
Age plus...
It's age divided by age. It's mental age divided by chronological age. Well, those are 2 measurements, aren't they? That makes it continuous. That means we can't count it. So that means we can't do anything with IQ here, or LDL, or heart rate, or drug medication. Does this schizophrenic drug work better than that schizophrenic drug? Only way to check is to take measurements, and then we can't compare them using this, so we're SOL. No, not at all. What you got to do is you have to have a curve that can deal with it. No, that's why, Joey, I know it seems like just more work, but just realize this curve is the next 2 weeks of our life together. I mean, seriously, we're going to stay in here. This is the rest of the class, is this idea. Is that fair? We spent 2 weeks with this, 2 weeks with this.
We're even.
That's it. That's it.
I'm ready to
That's
go.
all downhill.
I said then we're sliding into home.
Oh yeah, we're starting the slide today. This is the beginning of that slide into home. Seriously.
I don't like it.
That's okay, you don't have to like it. I think you will more as we go. Now here's the deal. If you have discrete data, do it this way. If you have continuous data, here's how we deal with it. We draw a number line. Riley, there's your infinity symbols, if you will. Arrowheads. That lets us know it goes on forever. Now, some people argue that maybe they both should not go on forever. For example, times of eye contact with schizophrenic patients, that technically shouldn't go negative, right? You can't have negative time. It should stop at 0. But it can go off infinitely that way. So there are limitations, but in a pure continuous distribution, it's going to have arrowheads going both ways. Terry, ask me that question.
Can we write this
Eye
down?
contact could go on forever.
Theoretically, it could. Well, no, here's the deal though, but theoretically it could go on forever. Just like theoretically, think about it this way, you could flip a fair coin infinitely and always get tails.
Yeah.
Right? Think about that Plinko game that you just watched Max watching in OBSI. They stopped the machine out at like 4 standard deviations. That doesn't mean it couldn't have gone further, but if a ball ends up over there, the machine itself is going to keep the ball contained. That doesn't mean it couldn't go further. It reminds me of, have you ever read the book Jurassic Park? Not watched the movie, but read the book Jurassic Park?
Yes.
There's a great line in there when they're trying to track the dinosaurs on the island. And they say, well, we made 100 Tyrannosaurs. And they go out and they count, look, I counted 100 Tyrannosaurs. And the mathematician goes, did you count everything you saw, or did you stop counting at 100? It's like, we stopped counting at 100, why would you count more? Because they had babies, there are more. So what you did was you saw exactly what you were expecting to see and didn't allow for the other possibility. There might be other possibilities, but if you build the construct so that it doesn't allow that, you're never going to see the extremes, which might be very telling. Does that make sense? Good, good, Tara. Please, Riley.
Can we write this down?
Oh, yes, please do. I'm sorry. Yes, please do. Please, I'm sorry.
We're just monkeys. We do what we're told.
Sorry, I'm sorry. Yes, please start writing. If you are writing, yes. So now, here's the deal. Here's the deal. Where will the X's now go? Yes, you got it, Alicia. The X's are going to go on the number line. So for example, you can slap that 0 right there. And you can slap the 1 right there. And now you've allowed for the infinitude of numbers between them. There's a half, there's a quarter, there's an 8, there's a 16th, and so forth and so on and so forth and so on. You've allowed for 2, you've allowed for 3, you've allowed for -1, -2, a little further, -3. Now, nobody said that you have to put 0 here. You can put any number you want right there. Any number you want can go there. Next week, I'll give you a couple examples of the numbers that are going to go there. One number is 100. We're going to put 100 there. You know why? Because we're going to analyze...
Math.
Say that again.
Math.
Max.
Oh, no.
Not max or math in general.
IQ.
IQ. We're going to analyze IQ. What you do on a bell curve is you put the average in the middle.
It's a U.
Son.
Oh,
Oh.
it is. That's a U. Hang on.
You already have a U after the end.
There's 2 U's. There's a U, O, U, S.
Oh, yeah.
I think.
Yes.
Yes.
Okay.
Sure.
Thank you. I don't trust my spelling either. I'm glad you guys don't either. So, now, realize you can go out further than 3 and down further than -3. That's the arrowheads, that's the infinities. But the idea is most of the data is not going to go out any further. So next week, we're going to have, for example, an IQ scale. And you can put this too if you want in your notes. Sorry, Ian, it's good to bring that up, honestly. Because I always hesitate to put too much on the board, because I know you write that down. And if you go back and look at it later, you're like, I don't understand why all this is together. So I try to space it out. You can have an IQ scale that will have 100 in the middle. And then instead of having 1, 2, and 3, you're going to have 115, 130, 145. This will drop to 85, and then 70, and then 55. So, in other words, you're going to have different scales for different applications.
Like the bar curve.
Hey, Riley, go.
Are we going to test around IQ today?
I don't know how to do that effectively. I do recommend that you guys take online IQ tests because they're fun. And since you guys are pretty logical thinkers, you'll probably score pretty high on them. Yeah, I don't know how IQ is tested. I think IQ is biased towards those that are logical and mathematical and pretty grammatical. I've noticed most of the questions on IQ tests that I've taken are pattern recognition. Have you ever done like the Elevate app? The Train Your Brain apps like Luminosity or Elevate, they're all freebies, I think.
Yes.
They're similar to that in that, can you find the grammatical error in the sentence? Or if this and then this and then this, what comes next? And they give you a bunch of choices to fill in the gap. And I usually do pretty good at that because I'm kind of like a logical, mathematical person. And I bet you guys would probably score pretty well. I have no idea what it's testing, though. That's the idea, right? Like, I don't know what is it testing my ability to take an IQ test? Or is it testing my intelligence? In which case, what is intelligence? I mean, then we have to have a cup of coffee and talk about that because I have no idea what. Well, that's not part of the class, though, unfortunately. So now there's that. But then you can have another application. So another application, not IQ. Say it's speed limits. Suppose the police are trying to decide. This is the in-class quiz I'm going to have for you guys to do next week. The in-class quiz is going to be based around the speed limits. Let me look at it real quick. In Portland, I believe is the one I did. Yep. An average of 71. So the 71 will be in the middle. That doesn't mean the speed limit's 71. It means that cars are averaging 71 on a certain stretch of road. And then you're going to go up to 79. And then you're going to go up to 87. And then you're going to go to 95. And you're going to go down to... Go ahead, Riley.
Why do you choose 79?
I'm not choosing anything. Hold that thought. Thank you, sister. Hold that thought. Hold that thought. We're going to answer all these questions in just a second. But I got to do subtraction first. 71 minus 8 is 63, right?
So it's
Minus 8 is 55.
Yep.
Minus 8 is
47.
7. Thank you. So Riley just asked a fantastic question that I want to address right now. Why did I choose 71 to 79?
Well, 71's the average, then how did you get
Good,
79?
good. Thank you. This is a fantastic question, Alicia.
Is it the next average outside of that? So like the next one that occurs.
What do you talk? What phrase do we use with outside of an average? It's the stand. Oh, good. If you get too far, it's an outlier. But in general, anything off the average is a deviant from the average.
Standard deviation.
It's a standard deviation. So the standard deviation of a speed limit is 8 miles an hour. 8 up,
Right
8
there.
up, 8 up. We did this earlier with the 95, right? 8 down, 8 down,
Right down.
8 down, right? With IQ, can you identify what it is? It's 15. 15, 15, 15. Assuming I did the math right, which I think I did. So every continuous bell-shaped, bell behavior data set has an average, which is the middle, thank you sister, and it's got a plus or minus around that average, and you have to know those two. Those are called the parameters. Remember how the binomial had two parameters? It had number of fixed trials and probability of success, two parameters. There are two parameters here too. You got to know the average and the standard deviation. Now what makes it messy at first is that every single time you want to analyze a data set, you have to figure out the curve for that data set, because that curve has an average and a standard deviation, which means you have to basically redraw the bell curve every single time. But you don't, because of the beauty of mathematics. You don't have to redraw the bell curve every time. That's why I started with this one right here. Now these would be, this whole question started with where do the x's go? And Alicia told me they go here. So the x's here would be x's 55, 70, 85, 100, 115, and so forth. The x's here would be 47, 55, 63, 71.
And where's the P of X?
We'll get into that. Give me 5 minutes, maybe. Maybe we're almost there, Riley. Thank you. Did you hear a question? Where's the P of X? It's a fantastic question, right? We'll get to that, I promise. This scale right here, they don't call them X's in mathematics. I don't know why, but they call them Z's. They're called Z-scores. I don't know why. They just are. It's one of those things. Why do they use exclamation point? Not really sure. I'm sure there's a reason for it historically. Because math, hashtag because math. I'm guessing. But the scales on that, or the numbers on that scale are called Z-scores. Faith, go. They're called Z-scores. Any number on this horizontal scale is called a Z-score. These are called raw scores or X-scores, and we'll get to those on Monday. Let's just let those go for right now. Anything below, anything in color, let it go. We'll come back to that in context. Once you know how to deal with Z-scores, everything else is a piece of cake. So for some reason, they're called Z-scores. Now, I only drew 7 of them on here. How many of them are there? There are infinitely many of them, because I only drew the integral ones, and I only drew the ones that you guys have already talked about. 1 standard deviation, 2 standard deviations, 3. See the standard deviations?
So is it Z to the n?
That's the standard deviation. -1 to 1. 2, thank you. 2 standard deviations. 3. Good! Half of a standard deviation. I'm making it tricky on you.
Before.
About 2/3. I was going for 2/3. I'm a bastard. Only because 2/3 of a standard deviation is 50% of the data. Remember the box of whisker plots from back in the day? 50% of the data was in the box. You'd have to go out 2/3 of a standard deviation to capture that box in a bell curve. So we'll come back to that. That was a bastard move right now. So the idea then is, we now have a great idea. For the standard normal, I'm going to start making a little laundry list over here. For the standard normal, it's called the standard normal. That's terrible. That's awful. That's an R. There we go. For the standard normal distribution, this is going to be our buddy for the last 4 classes we are together. Next week and the week after. The standard normal. Normal being bell curve, standard bell curve. There's lots of bell curves in research, whether it's social, whether it's psych, whether it's HDFS, whether it's natural resources, with exercise science. I tell you guys, I got an email last week from an exercise science PhD student who wants me to run some math for her. I'm testing this hormonal thing and I got to see the numbers. I don't know what to do. This is why you guys will always have jobs if you choose to go into statistics. Nobody understands it. You guys do. It's awesome.
Why you will always hear from us.
That's okay. I love that. I never had her in class. She's working at her doctor, but please, I'm here.
Julie Downey.
It's not Julie's. I've done that for her before too. She's the one that farms my name out.
I figured
She farms my name out. Oh, Sean, you love Sean. So pleasant to work with. Like, Julie, I don't sleep as it is. Anyway. Next time you see her, call her Ninja and go like this.
Oh, I don't get to see
You don't get to see her?
I'm, okay.
Who knows Julie Downey? Julie Downey, HHP. Next time you see her, and if you really, give her one of those. She loves that. The average of the standard normal distribution The average of the standard normal is 0. The average of any other normal distribution will not be 0. It'll be 100, or it'll be 266 for pregnancy, or it'll be 71 for speed limits, or it'll be 12% for flu rates. Go ahead, or it'll be
120 for systolic.
120 for systolic. Good, good. Every one of those has an average. But the standard normal distribution is going to average at 0. And the good news is we can change any other one and make it be standard normal via a transformation. We'll learn that on Monday. We'll talk about that right now. Let's talk about the standard normal distribution. Okay? The standard deviation, as you just figured out, is 1. By definition, we've defined it to be 1. It's very important. Good so far? Good. I'm just synopsizing what you guys have discovered on your own already, which is great. Riley and you guys have already picked out the z-scores. The z-scores, I'm going to see if you guys like this before you write it. Do you like this? I put z-scores correlate to the x's in the discrete distribution. Is that okay? Is that okay? We can rewrite it a different way. I'm trying to draw the parallel. Again, Joanne, not to change the gears completely, to show you the correlation. It's the same thing as the left column in the discrete distributions, right? The horizontal z-scores are acting the same. They're the data, if you will. It's the data. Does that make sense? The data is in the x column. These guys are really the data.
But, so is it correlated or is it represents the X?
Potato, potato?
Okay.
Does that make sense? Yes, if you like represents better, use represents. Riley, I haven't answered your question yet, I promise. I'm going to get to it. Because you're still thinking about the p of x's, aren't you? Good, good. We haven't gotten there yet.
Sure.
Oh, please, let me.
Why do we have the standard deviation of 1?
By definition, we have made it. This goes back to why you use the exclamation point for the factorial. We have made this be 1 standard deviation. We could have made it be pi, but we chose 1. Why? Well, 1's easier to use, first of all.
Sure, okay.
So we've normalized it. You'll often hear of normalized data in the world. We get data and normalize it. It's to make it fit this curve.
Gotcha.
So it's by definition for now.
Okay.
Now we can take care of that with Riley's question soon. We're getting to that, I promise. I'm not going to leave you hanging. Other questions? Is that sentence okay? That's okay. Thank you. Now, Riley's question. I promised you 5. It took 6. I apologize. Where are the p of x's?
Current.
Yes! You guys got it! You guys got it. It's the y values that you don't see yet. It's the bell curve. The bell curve is going to be the p of x values. How high the curve is represents the probability of that particular event happening. So in other words, we have to draw it in. Now, please, I'm going to try to draw this carefully, but don't be too harsh judgmentally. I want to draw this thing because I know that, number 1, 68% of the curve has to be between -1 and 1, right? 95 has to be between -2 and 2, and almost 100% of it has to be between -3 and 3. But it also has to have tails that go off infinitely. So be kind.
Rewind.
Well, that too.
Start over.
Oh, I don't like it.
That's actually kind of good.
Nice.
Oh, Ian, thank you! I've never gotten applause before. Thank you. 20 years of teaching, never got an applause for that. Ha! Very nice, my friend. That's the p of x's, Riley. Each event, so the p of let's write that over there as a note. This is kind of like a guidelines of the distribution. For this is the only continuous one we're going to analyze in this class. We'll get a lot more in 244 when we need it. We don't need it yet. The bell, if you can handle a bell curve at 243, 244 is going to be a breeze because you're like, oh, it's the f distribution, whatever. I totally got it because it makes sense because I understand the z distribution. So the z-scores correlate to the x's. The bell curve itself. Can I use correlate? Is that okay? Okay. Or represents, that works too, Faith.
I'll write it on mine.
That's okay. And in particular, the height of the bell curve. How high the bell curve is correlates with how likely that event is. This is why I got you guys drawing histograms in week 3. I wanted you drawing histograms to get used to the modes the most likely events being the tallest. I was trying to seed that like 2/3 of the course ago. So that when we get to this, which is by and large probably one of the most important things we do, is being able to look at a graph like this and get stuff off of it. I want you to be able to understand what's the most likely event in this curve. What value, which z-score is the most likely value? 0, because it's the highest. That means I drew it somewhat well, because I drew the highest point at 0.
What's
Good.
the average?
That's the average. Yeah. Good, is that fair? Is that fair?
Now,
Faith,
I'm
good?
thinking like the chickens would have been.
Good! If the chickens were 50-50, it would have looked just like this. But there weren't, they were 90-10, which makes it a skewed distribution.
So
Go.
then your 90-10, like on this line, it would have been, that 0 wouldn't have been 0, that 0 for it to be.
Correct.
It would have been the 0.9.
I wouldn't use this curve to talk about that, even if it was continuous data, because it's too highly skewed. Go ahead, Alicia. You're gonna say that. And we have plans to deal with that, even deal with that skew in 244. One of the first things we do with the 244 is, what if it's highly skewed and we still want to force a bell curve? We can do it. We have to change the sampling methodology. We can do it, but let's not get too ahead of ourselves. Thank you for making the connection, though.
Is it like Sarah Palin's?
Yes, very much like Sarah Palin's. If you did Sarah Palin's quiz, that curve looked almost identical to this, except the average was 31.
31.
And the standard deviation, I think, was 4.
4.
4! That's another, we could have put Sarah Palin down here, right? 31, 35, 39, and so forth and so on.
I'm like, okay.
I did it right! Of course you did it right! I didn't number the damn questions, I apologize for that. Hate when I'm dumb. That's okay, we'll figure it out.
No, I did 8, or I did 1, 2, 3, but.
Oh, thank you. I apologize. I'll go back and fix that over the Christmas break when I have some time to do some edits. So the idea is, all of these scores have a probability. Clearly 0 is the highest. It's the highest point on the curve. What else do you notice about the curve? It's perfectly symmetric. Thank you. So not only is 0 the average, it's also the
Mean, median, mode.
Thank you. It's the mean and the median and the mode. Since it's the, what? Since it's, now, you knew this already. Because when we talked about it back in week 3, when you got symmetric unimodal data, all 3 are basically the same. You knew this. You knew this. Now the question is, I do have a question for you. So we know that 0 is the most likely, right? What is that likelihood? What's the number attached with that? Like with chickens, we can calculate it, right?
We don't have.
Like it would be, say that again.
We don't have the information we can.
Good. Now, believe it or not, you do.
No, it's just.
Not right now. Not with this picture. Correct, Riley, you don't. With this picture, you do not. Do you remember the picture of Carl Friedrich Gauss on the 10-mark bill that was up there?
Sure. Yeah.
Did you see the equation that was with it?
That was like saying.
Hang on.
Money